Welcome back everyone. So, we are starting NPTEL course on topological phases of matter, and in this chapter we are looking into various symmetries, and in last class we talked about internal we talked about inversion symmetry and how the inversion symmetry will manifest both in space time for odd dimensions and even dimension. And then we talked about how various common operators will transform under inversion. And then we talked about a state in position representation. It will move from position x to minus x, or in the momentum space it also changes p to minus p, and you can recheck this with a Fourier transformation starting from one state in the position space and go to the momentum space or vice versa, and you can see that this conclusion holds. Now, in the previous example we just took one state, one sort of wave function, but now let us take a spinor of a state which sort of defined in some basis called sublattice basis. Okay. And we will generally call it parity. So, parity and inversion are often sort of talked about together, and it is a matter of nomenclature, and it has to be defined as it is defined. For example, for harmonic oscillator case we say that the wave function has parity, and that is pretty much when we looked into the inversion symmetry. So, under the inversion the wave function at plus x or minus x, whether they are same or opposite, right, and that we call it even parity and odd parity. And in some cases, some lattice, for example in hexagonal lattice, so we know that let us start from some center, and we know that at different lattice sites you have different sublattices. We talked about this in the case of graphene, saying that you do not have a Bravais lattice, honeycomb lattice is not a Bravais lattice. So, you need to start with a triangular lattice, triangular like lattice, and with two basis states which are generally called sublattices. So, in this case we have A and B, and if I choose a coordinate system like this in 2D, x and y. Okay. So, at point R where you have a sublattice A, if I go to minus R, and I am taking it to be minus x and minus y, we see that the basis has changed. So, now the definition of inversion symmetry has to take into account the fact that we change x and y to minus x and minus y, or even if you want to take this as your inversion, which more appropriately it should be the case, or even here, yeah, let us take this one or this one. We see that as we make the rotation in the space, we also have to make one more rotation in the frame, in the wave function, which is written as a spinor of two bases. So, under inversion or A has to go to B minus R and B has to go to A. So, now we see that the rotation requires both, the inversion or parity requires both a change in the internal symmetry, which we will call sublattice symmetry, and as well as space time. Right. So, what can be a unitary operator acting on this basis, this 2 by 2 operator in this 2 by 1 vector? What that would be? It will simply be A has to go to B. So, it will be somewhere here and here and there. This is just a sigma x operator. So, then the unitary operator acting on the representations of the state under inversion or parity will look like this: ui is sigma x and go to So, will is related to psi at minus r. So, r goes to minus r, we probably have to just put by hand. There is no operator representation for this, but this one is a representation we just talked about. If we choose the position coordinate, it will change. And within the state, if it is a spinner, whether there will be rotation or not, that is what has to be captured by an additional unitary operator that acts on the local Hilbert space between the frame. Okay. So, this will be the parity operator for this sort of lattice. So, time reversal symmetry. T goes to minus T by definition. I will make a caveat here. So, T is generally, unlike these cases where they were operator and it changes under symmetry, but T is strictly speaking not an operator. It is not a dynamic, time is not a dynamical variable. So, T is not an operator. So, it is a scalar. So, however, we often just write it as a T goes to minus T, but it is not the time, but the arrow of time, the direction of change of time, that changes under time reversal symmetry. It is the arrow of time, or sometimes simply the thing that involves dt changes to minus dt. Okay. So, position do not change under time reversal, but the momentum changes because it has the time in the denominator. So, the electric field does not change, but the magnetic field would change because L changes to minus L and spin changes to minus spin. Okay. This is how the things, the operator and the coordinates and the momentum, they will change. In another thing, under time reversal is I has to go to minus I. So, time reversal operation cannot be obtained by a unitary operator. It requires an anti-unitary operator, and it can be justified in many ways, and we can just take one example, that should be enough, is that look at the position operator. Okay. So, you see that under time reversal, position operator has to change to minus p, but x do not change. So, I must change. Okay. And even the dynamical evolution of a state as t goes to minus t, the direction of time, the dynamical phase also has to change, and that is being accommodated by changing I goes to minus I, since t do not change. Okay. So, that these two examples should be good enough for us to take I to be 2 goes to minus I for time reversal symmetry. So, which says that time reversal symmetry T can have a unitary part which will act on the state, as we did it for inversion or parity. There can be a unitary part. On top of it, we need a complex conjugation operator which will change I to minus I for every wherever I appears. Okay. This is unitary. Now, how the state will change? So, we can write it the same way in the position space or in the momentum space. Okay. So, now if I apply time reversal operator, so it will be like here, and then I can apply T inverse T inverse T here, and the same thing here T and T inverse T being identity, we can always insert there. So, what we will have is, in whatever the x psi star because of the complex conjugation, whereas x remain x, and time reversal acting on state x does not do anything. So, it will be x. Whereas, for the momentum's case, if you do the same way, you will see that it will be minus p t by a change of variable. Okay. So, a state in position space under time reversal, you get a complex conjugation of that state at the same position, but in the momentum space under time reversal, you get a complex conjugation, but also goes from the other part of the Brillouin zone, minus p. Okay. What about spin? So, what we can do is that we can just do it for any spin or any total angular momentum. Let us take any total angular momentum and which can be linear momentum, spin, or their combination. So, whatever I am going to derive for time reversal, it will just act it will be valid for any angular momentum, and this is the z component. That is how we define, right. And any sort of abstract state we can again define in terms of some space time coordinate, and here these are being angular variable, angular momentum. So, we can define, we can expand them in the theta and phi angular variable, and these are being the wave function. This is the solid angle defined in the angular variable. Okay. So, that is how abstract angular momentum state can be expanded as an example. And so, now acting T, what we will find is, so again so T y m j T inverse T theta phi, in the special coordinate theta phi does not do anything. So, this one what we can do is that we can just go into their expression, general expression, and under time reversal what we will find is that it changes to star. And this is equal to y j minus m. Okay. Times minus 1. So, I may have made a mistake. Yeah. So, I am, let me write it, j minus m y minus m j, and at theta phi. So, y j m theta phi under time reversal changes to minus 1 j minus m So, in the abstract state okay. That is how any angular momentum state will transform. Now, if we apply twice, so the first one gives us minus m, j minus m acting on j minus m. If I apply twice, this one acting on j gives you minus 1 j remains j, and it has to change m to minus m, right. So, now minus m, so it will go back to plus m, which gives us minus m to the power 2 j. So, this gives us the most important property of time reversal for spin systems. So, when j is integer, such as spin 1 or linear angular momentum, then we get t square equal to minus 1 square equal to plus 1. So, you do not have any Cramer's degeneracy, but when j equal to half integer, for example, spin half electrons that we are interested in, you will have t square equal to minus 1 2 times half gives us minus 1. Okay. So, let me rewrite it. For spin half electron, t square equal to minus 1. And that is consistent with the fact that, so when you apply t twice on a state, so we have some spinner, some spin state, we apply it once and then it sort of goes to some other state, and if it is up spin state it goes to down spin, and that is what it is, right. If it is a up spin state, so that is always the case. If it is a up spin state, it will always go to down spin under time reversal, even for integer values or half integer values, or even for angular momentum also. Only for integer angular momentum, when m equal to 0, then it will change, but otherwise if it is up spin it will go to down spin, and for spin half you only have up spin and down spin. But now you see something interesting here. If I do that algebra, what we will find is that time reversal acting on half half, which we will call up spin, goes to half minus half, which is our down spin, and t acting on down spin will however go to minus up spin. And this is consistent with the fact that so when you make when you apply time reversal, an up spin goes to down spin, whereas a down spin goes to minus of up spin, right. So, that then when we apply twice on the same spin, it first flip the spin, then we flip the spin again with an opposite sign. So, we get back to the same spin, but with the opposite sign, and that is consistent with the pi rotation of a fermions, right. If you make a 2 pi rotation of a fermion, the electron or the fermion comes back of, let us talk about electrons only, spin half, it comes back to the same state, but with a phase of pi, and that is also consistent with the time reversal operator, that under a spin rotation. So, it is like you are sort of, you started with a up spin, and by applying time reversal operator twice, you actually have wrapped that up spin around a down spin, because at some point it went to a down spin and then again it come back to an up spin, right. So, it is like you have wrapped that, or you have sort of rotated that up spin around another down spin electron or another electron. And from exclusion statistics, we are supposed to get a phase of pi, and that is consistent with this. So, a typical time reversal operator for spin half case. So, we would denote it by some up spin and down spin. So, under time reversal we are supposed to get down spin and up spin with a minus sign. So, time reversal so let us do the first the wave function one. So, it must then be the spinor basis, its up goes to down 1 and minus 1 and a complex conjugation. So, this is the unitary part, and you have a complex conjugation. So, this one is obtained by sigma y times I. This gives me this operator times this. And this is also all consistent with the fact that T square equal to I sigma y complex conjugation I sigma y complex conjugation. So, let us keep this I sigma y, and this one under complex conjugation sigma y remains sigma y with a minus sign. And I goes to minus I. Okay. So, we get I sigma y so equal to I square sigma y square equal to minus 1 sigma y square equal to 1. So, this is this. So, it is consistent with the T square equal to minus 1. Okay. Finally, Cramer's degeneracy for spin hub. Okay. So, I have some Hamiltonian acting on some block state and in momentum space P gives you a band at a given momentum okay, where P is equal to h cut k is the wave vector. This is how a band structure is defined, right. Now, if I apply the time reversal operator, or let me even do it this way. T, T1 P, this one is supposed to give us E star minus P psi P, and here they commute and energy eigenvalues are real. So, in general it looks like there is no degeneracy, because it maps a energy eigenvalue at P to minus P, right. And these two states are sort of defined at different momentum, because this will also take you to minus P. But in Brillouin zone there are special points where P is equal to minus P. Let us take a square lattice. Kx, Ky, and those points are gamma point, k equal to 0 or p equal to 0, and also these points, these high symmetric points. This is the gamma point, high symmetric points. So, this point whose minus k is this one, but these two are related to each other by at reciprocal lattice vectors. So, which means at gamma and high symmetry points, k points, E p is equal to E minus p, which means psi at p and psi and minus p or p, both the same, are degenerate, and we have already proved that these two states when t square equal to minus 1 are orthogonal, and now we showed that they are also the same energy. So, they are degenerate. At every other k point they do not have to be. So, if I draw a band structure and at minus pi in 1D pi, and let us put some band structure let us say this is for up spin. The band structure for down spin must then be degenerate here, and it does not have to be degenerate here, but it also again has to be degenerate here, and then it again has to be degenerate here, and this is for down spin. So, these points are called Cramer's degenerate points, okay, and these are also. Okay. So, we understand the symmetries, and now we understand how that symmetry, under symmetry the states will transform under various symmetries, and we also looked into in details how the spin half especially will transform under time reversal, and the important part is that for spin half t square equal to -1, and that gave rise to a degeneracy at all the high symmetry k points, whereas they do not necessarily have to be degenerate at other points. Now, if I have, this is a homework, if I have inversion which make all energy at plus k equal to at minus k, and also time reversal which will make these two states to be orthogonal. So, all points then must be degenerate. Show that all k points are degenerate. So, this is a homework. Okay. So, with that we will conclude here for this part of this course, and in the next class we will start with second quantizations. Okay. Thank you very much.